Okay, so in this next series of videos, we're going to be going through the information in section 6.4. Specifically, we're going to be talking about logarithmic equations and inequalities. And really our main goal here is just to learn the strategies that are involved in solving these equations and inequalities when a logarithm or logarithmic function is involved in our function we're trying to solve. So we're going to be doing lots of examples, but we're going to be revisiting a lot of the properties and important aspects and characteristics of logarithmic functions that we've talked about in previous sections in chapter 6. So let's actually start by looking at a few of the properties that we're going to be using quite a bit in these next few videos. So these are the top 5 that we'll be hitting today. So I wanted to kind of go through and to take a look at these. So number 1, real quick, this is how we defined a logarithmic function. So if we know that the log base b of x is equal to c, another way that we could think about this is we could write this as an exponential equation. So we could consider that x, the argument inside of our logarithm, is going to be equal to our base b raised to the power of c. So this is a way for us to translate between a logarithmic expression and an exponential expression. Number 2, given we have some function log base b of x, we know that the domain of this function is x has to be strictly greater than 0. Now this isn't necessarily just about x, we're talking about what's inside of our logarithm. We're talking about the argument inside of there. So another way we could think about this is if we had the log base b of something like 4 minus 7x. Specifically, it's the argument inside that has to be strictly greater than 0. So in this case, 4 minus 7x would have to be strictly greater than 0. We could then go about solving this for x to think about or identify the specific restrictions on x. So if we moved 7 and then we divide by 7, and we'd get 4/7. So x would have to be strictly less than 4/7 in this case, just as a quick side example. So we always want to watch out for this, as we'll see with these next ones. If we have the sum of two logs with the same base, we can rewrite these as the log of the product, so x times y. And if we have the difference of two logs with the same base, we can rewrite this as the log base b of the quotient of x divided by y. And then lastly, if we have log base b of some expression raised to some power r, we can rewrite this by moving the exponent as a coefficient, and we've got log base b of just x. So these are some properties that we've already spent some time looking at in section 6.2, but we're going to be using a lot today. Okay, so let's take a look at an example of how we can start to use these. So let's consider the logarithmic equation log of 3x minus 1 is equal to the log of 4 minus x. And what we're going to do here is we're first going to determine the restrictions that exist on x in this particular equation, and then we're going to go ahead and try and solve for x. Okay, so let's deal with part A first. So in part A, we're going to look at the two individual logarithmic expressions to determine what our restriction on x is going to be. So the first off was we've got the log of 3x minus 1. Now what this tells us is that the argument of this logarithm, the 3x minus 1, this has to be strictly greater than 0. And if we were to continue solving for this as an inequality, we would see that based on this logarithm, x is restricted as a number that has to be strictly greater than 1/3. Now, the other restriction we're going to have to consider is the one based on this second logarithmic expression, which is the log of 4 minus x. We have the exact same setup. The argument has to be strictly greater than 0 inside the log, and if we were to solve this, we'd have what minus x has to be greater than minus 4, and if we multiplied both sides by a negative 1, we'd see that x has to be less than positive 4. Now, the restriction on x for in terms of solutions for this equation is going to be the combination of these two restrictions. So it's going to be this restriction and this other restriction. One way you could maybe think about it is by drawing a real number line, and we could actually see our solutions. So we've got 1/3 and we've got 4. So if we were to think about numbers we're including, well, it's all the numbers strictly greater than 1/3 and strictly less than 4, and we're not including any of these. So the overlapping interval is going to be all of the values in between these two numbers. So in terms of this equation that we've got going on, our solutions must come from this interval. So our solutions must come from this interval. You don't always have to draw it out. Sometimes it's easy enough just to look at the algebraic representations, but this is one way we could think about it. Okay, so those are our restrictions on x. It has to be in between those two numbers. So now let's address part B, and in part B we're going to actually go ahead and solve this. So we're going to consider something in this case. So if the log of 3x minus 1 is equal to the log of 4 minus x. Since we have the same base here, both of these are the common log, so we have the same base. So since the bases are the same, or since we have common bases, what we can actually do is, in order for these two logarithms to be equal, their inner arguments would have to be the same. So in this particular case, we can go ahead and we can say then 3x minus 1 has to be equal to 4 minus x. These have to be equal in order for us to maintain the original argument. So now we can just go ahead and take this and solve this equation for x. I'm going to go ahead and get all my x's on one side and my constants on the other side. So I'm going to add x to both sides. I'm going to add 1 to both sides. And if I do that, I'm going to have 4x is equal to 5, or x is equal to 5/4, so like 1.25. And that would be our solution. We are going to want to double check that this solution does fall within the restrictions that we've put on x. So if we were to go back up to our original restrictions, 1.25 or 5/4 would be sitting right here in the sweet spot of this interval. So we're good to go in terms of this being a solution for our equation. Okay, and this is not an uncommon approach. If we were to look at this equation and say what we have is we have only logs involved in our equation. We'll see more of this as we do some more examples, but it's worth noting that this approach followed suit after having an equation with only log functions. Okay, so let's look at another example here. Let's say we were asked to solve for this equation. 2 times the log base 3 of x minus 5 is equal to 3. Now something to note here as we move on is that this equation has logs and constants. So something to keep in mind. Another thing, we don't have to make this a whole part, but we can look at this and we can make note of the restrictions on our x values. Now, in particular here, the argument inside our logarithm is just x. So we know that x has to be strictly greater than 0. So all of our solutions should also fall under that restriction. Okay, so let's just go ahead and solve this. So something to note. And if we go through, the first thing we should really do in a case like this is isolate the logarithm. They're going to see a lot of parallels between how we approach solving logarithmic equations and exponential equations from the last section. So first thing we're going to do is we should isolate the logarithm. Which we can do in in this case. We can't always do that. So we're going to move that other constant, that 5, to their sides. So if we add 5 to both sides, we'll have 2 times the log base 3 of x is equal to 8. And while we're at it, in order to isolate this log, we should also remove any coefficients that happen to exist. So if we divide both sides by 2, we're going to get an isolated log base 3 of x is equal to 4. Now, in order for us to solve for x, we're going to go back and use the first property of logarithms that we discussed just a moment ago, and this allows us to rewrite this log equation as an exponential equation. So next, we rewrite this as an exponential equation. And this is going to give us our solution, as we'll see in a second. So if we rewrite this as an exponential equation using property 1, we know that if the log base 3 of x is equal to 4, that x has to be equal to 3 raised to the power of 4. More specifically, x is going to have to be equal to 81. So that would be our solution for x. We double check that this is within our domain, and since our restriction is just x has to be strictly positive, then this does check out, and this is going to be our solution. Okay, so those were two pretty straightforward ones that we want to look at. And what we can do is, before we move on to the next videos, we can go ahead and, based on what we've done here, we can sort of outline a general method for solving equations with logarithms. As we saw, if possible, the first thing that we're going to want to do is isolate the logarithmic function. Now, isolating the logarithmic function, if possible, could mean one of two things. This might mean 1 log on each side, like our first example, or it could be 1 log on one side and a constant on the other. So this is going to sort of be our initial goal, and this isn't always going to work, but this is usually what we can go for. Secondly, once we get this, if convenient, we're going to express both sides as logs with a common base, then set the arguments equal to each other. This is normally something that we'll see if we've got only logs involved, which we saw with our first example. Otherwise, if we can't do this, we're going to need to rewrite the equation, the log equation, as an exponential equation. This we'll usually see when we have logs and constants. And we're going to do plenty more examples showing these, but we'll do that in the next video. And before we get to the next video, what I'd like you guys to try is this next one. So based on what we've done before, this should be pretty straightforward. Go ahead and solve this equation for x. We got 5 log base 4 of x plus 2 is equal to 17, and I'll give you guys the answer in the next video.